prepare the original agenda and participants, I have to disclose that a good friend of mine, Milan Brandt, couldn't make it today due to personal reasons, coming from Australia, but we have a perfect substitute. This is Martin Leary, also from RMIT, Dongdong from the Nanjing University of Aeronautics and Aerospace in Nanjing in China, and a good friend of mine. We know each other since, I don't know, 20 years, Tim, from Aachen, so please welcome to the stage. And we will be starting, because I know, of course, that in Australia it is a little bit later today. Martin, can you understand us? Can you hear us? So now we do experience, and we suffer from no, let's say, no audio at the moment. Hopefully we can fix it. Of course, I know that we are in Germany and we are not at the leading edge of digitalization. Just give us a second. Or are you muted? I don't know. Might be the error is with you. We still have the same issue, Martin. We still have the same issue here. Just give us a second. Or might be more than 1 second. Or if you guys from the technique just need more minutes, we can go on with the second first. That might be we can run with Dongdong first, so that you have enough time to fix that problem. Just give me a hint. Martin, say something. No, still the same problem. Okay, I think we should go on, because otherwise, so you have enough time to fix the problem. And if you can show, instead of Martin Leary right now, the second presentation of Dongdong, that would be, at least from my perspective, much appreciated. And Martin, you will run second, if that is okay for you.
Okay, thank you very much. Thank you very much for the invitation from Professor Kabasa. And also, thank you very much for the organizing committee of the conference. Yeah, I fly from Beijing to Germany 10 hours for the 10 minutes presentation.
and participation in our panel discussion afterwards.
Okay, thank you. The title is Material Structure Integrated Laser and Manufacturing of High Performance Medical Components. I'm from Nanjing University of Aeronautics and Astronautics. Currently, I think the additive manufacturing 3D printing, this is a very strategic key technology for the global technical innovation. Yeah, I see something about it in China. About 10 years ago, China Ministry of Science and Technology, we launched a very big national R&D program called Additive Manufacturing and Laser Manufacturing. We have 4 categories. Yeah. And then when we talk about laser-based additive manufacturing for medical components, basically we have 2 directions and 2 typical processes. The first one is for previously we called AMD, currently we call it LDD. Normally it can be used for large scale components. And then it's a powder bed-based silicon laser melting, SLM. Currently we call it LPBF. I think both these 2 processes have opened up new routes for design and manufacturing of the integrated components. When we talk about the powder bed-based LPBF process, it created in the late 1980s from the University Texas Austin. We call it silicon laser sintering. And then 25 years ago, from ILT, want to be produce the fully dense laser-based medical parts. And then also there are some support from optic, mechanical engineering, material science. Then selective laser melting this patent is issued in 2021. And I once had 2 years staying in Frankfurt ILT as the Humboldt Fellow. At that time, about 50 years ago, we used silicon melting to produce titanium-based nanocomponents. At that time, we can only produce very small cubes, But now we can produce very large components. I think there's a very huge technical leap during the past 25 years. And then when we talk about the little additive manufacturing, this is actually quite complicated. For the material, normally there's a lot of market structure issues, and for the process, normally there are some mesoscale, several hundred micrometer issues, and then for the structure and the components, there's normally it's a macro scale. So the core scientific challenge for the additive manufacturing, I think this is a very large and cross-scale coordination of the process and the affordability. And normally, for the conventional route for the additive manufacturing, first we design a structure, and then we choose the material, and then we use the process to fabricate the component. But normally, this is need a lot of try and error steps. And for the future, what we can do to achieve the high performance or the multifunctionality. And 3 years ago, we published a paper in Science. We have a new concept called material structure performance integrated additive manufacturing. So that means in integral components, we can print the different material and the innovative structure at the same time. So changing the conventional series mode to the petri mode. And how to understand the material MSPI. I think the first idea is to have the right materials printed in the right positions. For example, first level, we can print different components, the distribution, different phases in the alloy. And the second level, we can print different materials in different positions of the part. And in the future, we can even print the different functional electronics inside the metal components. So I think it will have a lot of issues for the material for the additive manufacturing. And also, I take this opportunity to report some results from my group in Nanjing. First issue is that we use the nanoscale ceramic to reinforce the aluminum alloy. We just added a titanium bond to the very common, conventional available aluminum silicon alloy. We use the nanoscale reinforcement to increase the strength. And then we can use different ceramics, because we know that the ceramic normally is very brittle, but we can combine two different ceramics to make the strength even higher. And then we can also print one layer ceramic and one layer of the metals to build the graded components. And the second feature, I think, is the unique structure printed for the unique functions. Currently, there are some very interesting structures that can be printed. For example, the topologic structure, cellular structure, and the buy-in structure. I think the design for additive manufacturing, this is a very important meaning to broaden the freedom and the benefits of AM technology. Especially for buy-in structure, this is very important because in nature there's a lot of very good structure that can be learned to realize the functionality of the components. I give two examples from my group. The first is that we produce the lattice structure, but we also introduce the node reinforce to make the lattice structure even stronger. And we design the structure and use the SEM to print it. And also we disclose the fracture mechanism of the printed structure. And also, we learn from the polymer pier to produce the very disordered structure. First, we use the micro CT to build the model, and then we use the 3D printing to print it. And this structure has a very good response to the energy absorption. Also, it has a very good thermal management property. And this conference is very industry-oriented. We also use this structure to produce the next generation of nano satellites. Because it has a very strong multifunction requirements, for example, the lightweight, load bearing, and the heat dissipation. And we use these buy-in structures to produce build the structure, make it load bearing, and also has a very good heat dissipation property. And also we use the 3D printing to print it and to build the 1U nano satellite. Finally, in the future, what we can do, I just make an example for the bio-inspired materials structure integrated manufacturing of the bottom component of the preliminary exploration lander. Because for the conventional way, to produce this lander, it is very complicated. And in the future, maybe we can use the 3D printing to print it. For example, for the main frame, we can use the topological optimization for the main structure, and then we can learn from the web of spider to produce the structure for the shock absorption, and for the outer structure for the tumor installation, we can learn from this comb to produce the whole structure, and then we use laser 3D printing to print it. And we have a very large machine to print the structure for the tumor protection. And also we use learn from the web spider to build the shock absorption structure. And finally, we can produce 1 meter that large structure for the main frame of the lander.
Hear me now? Just
okay. This is a final remark. And last year, I published one book by Elsevier. I think for successful application of additive manufacturing, we should explore more science behind manufacturing. I think in order to tailor a complicated laser additive manufacturing process, I think a complete fundamental understanding of the basic science behind the laser additive manufacturing process is very important for us for the future, for the success of the additive manufacturing production.
Checking this works.
That's all. This is my presentation. Thank you very much for your attention.
This works now. Checking this works now.
Thank you very much, Dongdong. The format will be that we will be having 3 consecutive presentations, each 10 minutes, and then afterwards discussing, let's say, country-specific, region-specific USPs from China, from Australia, from Germany on the future upcoming challenges of AM. So coming back, my friend, to Melbourne, hopefully we can hear you now. Say something, Martin.
So good to speak to you, I hope, Ingo.
It's so good to hear your voice. So, Martin, may I ask you to present your slides, and afterwards, as the third participant, Tim Biermann, will be showing his slides, and afterwards we will be discussing what was disclosed just a minute ago, the country and region-specific USPs and key differentiators. Martin, floor is yours.
Yeah. Absolutely, it would be my pleasure. Thank you so much for the invitation. I really wish that I could be with you, perhaps next time. As always, any of you and your colleagues are welcome to join us in our exemplary Centre for Additive Manufacturing in Melbourne. I know that Ingo has had a long connection to our additive manufacturing facility, so he can spruik on my behalf. I work for a university that focuses on applied outcomes. We have a large number of students, almost 100,000 students, many in health. So for instance, nursing is very important to us, many in engineering. In fact, more than 50% of our students are studying engineering of some kind, and it could be at a postdoc level, a PhD level, a bachelor's degree level, or a technical level. There are many, many engineers trained by our facility. It's been the focus of our university since it was established. More recently, we've been interested in scholarly research. The additive manufacturing facility that I'm going to introduce is really the university's commitment to that advanced technology, especially in connection to a local industry. So the Australian industry has particular requirements. It's quite unique. The government funding models are unique. The opportunities for sales, the customer base is particularly unique. it's a challenge to support that industry, especially given the isolation of Australia physically from locations like the markets of Europe and the technology centres of Europe. So we've essentially established quite a high value centre, built initially with $30 million Australian, and then supported quite substantially since day one when we opened sort of 15 years ago. And essentially this facility provides an additive manufacturing technology hub that we can use for research, of course. We can use for education of the next generation of engineers that will be designing for additive. And also we can provide an opportunity to engage with local industry to help them to uptake this technology without them having to spend their capital initially. So they can come and play with our hardware, play with our software, see what suits them, and then move on to commercial outcomes based on that. So we have a rolling range of AM hardware. We're not particularly interested in any type of material or any type of AM technology. As I said, we're interested in supporting local industry. So whether it's a polymer jetting system or a fused deposition modeling system, we need to be able to have that particular capability. But one of the facility research outcomes is particularly in the center of laser-based powder bed fusion. So for the past 15 years, we've had a fairly extensive complement of particularly SLM solutions, powder bed fusion machines, and we have at any one time 3 or 4 machines running, some for research where we can trial new powders, new geometries, new structures, and some for production where we, for example, have an SLM 500 that's continuously producing for our local industry and helping to support that particular sector. Our latest installed piece of hardware is the Economy MIDI Plus, and we're using that to develop new processing parameters, new methodologies for achieving metallurgical outcomes that aren't possible with other technologies. But also we're using the in situ sensing to support our predictive modeling and to be able to validate the numerical models that we build to do things like predict thermal fields in powder bed manufacture. A fairly broad discipline interest in our centre. So Ingo's extended collaboration with Professor Milan Brandt, who you'll know from his extensive contribution to the field of laser applications, and also a range of metallurgists in titanium and aluminium metallurgy, particularly Andrei Molotnikov in situ sensing of defects. I run the design theme, and we also have a modeling and a biomaterials theme. So it's a multidisciplinary center that essentially supports a number of academics, researchers, and as I said, a rolling complement of industry partners. So at any one time, we have about 20 full-time staff, academic staff embedded in the center. We each have at least a few PhDs and researchers, so that number sort of builds up to about 100 people connected to the building. And so it's quite a vibrant center. Lots of established professors down to students who are running particular projects and industry partners. It's a fun place to be, and we do some very interesting, serious research. The research that I'm particularly interested in, and for this reason I've selected some of the recent publications, is to do with cellular materials and opportunities for connecting the theoretically optimal cellular materials with what's limited by the AM technologies. So basically doing the best that we can with the AM technologies and building digital twins that can support that, and we've been very successful in that field. I've also included a couple of articles, these in fact from Nature, from my titanium metallurgy colleagues, and as I said, developing new alloy compositions and processing parameters that can take advantage of the powder bed fusion opportunity. Some of the industry outcomes that we've achieved recently, so there's a different outcomes. I put partly for humor's sake, but also partly for a serious example, implant that we recently made for a veterinary application. But it's a very good example of the kinds of work that we can do quite quickly, where we're able to take digital data, build candidate components, manufacture them in-house, connect with local hospitals for implantation, and then we can do in parallel all of the mechanical testing and computer tomography certification to confirm that the implant is as it should be. If you take a look on the left-hand side, something a little bit more connected to us as humans, we were a very pioneering team in the manufacture of just-in-time patient-specific cellular implants. And this is a very serious outcome that was achieved almost 10 years ago, where a lady had a vertebral defect and we built a generative tool. And this is 10 years ago to be able to build that very complicated ladder structure. And that was the start of our journey into medical additive in Melbourne. We often use our powder bed tools to build what we call billets on demand. So if you take a look in the center, you can see a very complicated geometry that is very much near net. There's much milling to be done, but this was part of a CubeSat outcome. So essentially we're building a complicated billet that then takes away a lot of the buy-to-fly challenges around, machining directly from very large billets. We connect to a very large number of local hospitals and important industries here in Australia. And perhaps during the conversation, we can talk about how the Australian industry is different to, say, the European industry, the Chinese industry. It's unique here in Australia, and we sort of attempt to rise to those local challenges. One of the substantial opportunities that we have with the Therapeutic Goods Association, which is our regulatory board, is that it's very favorable for the manufacture of custom implants, very much so in comparison to the regulations that you see in Europe, very distinct here in Australia. So we've really connected closely to the hospitals that are well regarded, and we've been able to educate our TGA on certification and essentially lead the way from those first implants through to these customized just-in-time implants where we're building them as the surgeon is undergoing surgery, and we're able to actually fabricate components on demand according to the particulars of the surgical need. This is a really fantastic outcome from our group, connected with some very large players in this field, in particular the surgical team in Melbourne, and of course Stryker Medical. We've got a number of patents in this particular area, and it's something that evolved since we initiated it, 10 years ago when I first sort of met you, I guess, Ingo. Another area that could be of interest particularly is defence. So we're a long way from Europe, a long way from some of the traditional suppliers. Maintenance of defence hardware is very important in Australia, and it's a very substantial challenge. So there's an opportunity for using additive for the manufacture of defence hardware, in particular hardware that is for armour purposes, particularly for the protection of personnel. This is something that we've been studying in detail, especially if we compare the ability for a metallic substance to arrest a bullet. There's a V50 number that's very, very important. And if you take a look at some of the standard AM powders manufactured in the standard way, they don't actually fare very well in those conditions compared to commercial titanium alloys. So over a number of years, we've looked at opportunities for taking advantage of the rapid solidification connected to powder bed fusion to modify process parameters to achieve the microstructural outcomes that we want. And directly off the machine, we've been able to achieve in the green here some numbers that are approaching those of commercial titanium alloys. So this is something that is an example of one of the research outcomes that connects to something that's important for the local industry. That's our focus here, from industry through to defined strategic research, and then all the way down to teaching at the undergraduate level, so that we can teach the next generation of engineers to use additive in an effective way. Looking forward to seeing anyone from the audience here in Melbourne. And thanks again, Ingo, for the opportunity to speak today.
Thanks a lot, Martin. So, ovation to yours. And please do not hang up, because you will be part of the panel afterwards, right? Do not hang up. We come to our third participant and third speaker. This is Tim Biermann. Tim, floor is yours.
Yeah, thank you very much. The focus of my presentation will be, as Ingo asked for, AM research topics in Germany. And thank you for setting me up to fail, because that's a pretty daunting task to complete in 10 minutes. So I'll try to do it in 5. But basically, why is it so daunting? Because as we saw already, the talks were focused on laser-based processes. And I, for myself, I'm coming from the laser-based processes. But to be honest, AM is so much more than those laser-based processes, as we learned about in this conference over the last 2 days. And so, as a good presenter, let's tailor the presentation to the audience. So please raise your hand. Are you in research? Then raise your hand. And who is an application, so applying it as an end user? So some of them are not using AM at all because they didn't raise their hand, so I can educate them as well. So basically, the interesting thing is, whenever we talk about that, first of all, I think we need to behold a little bit and see that we came a pretty long way. Because for the traditional milling, it was 200 years to come from an invention towards a machine looking like that. And in our world, and yes, it depends. So whenever you talk about SLA or whatever, it's a little bit earlier. Other ones were a little bit later. But let's say roughly 25, 30 years from the basic inventions to the machine today's. The end user actually sees a machine like this. It doesn't matter what kind of manufacturer, they sort of look the same, and it doesn't matter if it's a laser inside or an E-beam or is it bioenergetic or whatever. The customer expects all of them to perform at the same level. And therefore, it's all about promises. And I don't want to focus just on, let's say, like the laser-specific stuff, but the questions are, at the end of the day, what are the focus points, the cluster points, where all of the AM processes have some more, some less, areas where we are researching right now and where we try actually to get everybody to the next level. And at the end of the day, looking at the process chains, like from the CAD/CAM to the final part, and looking for the AM process as well, including monitoring, big data, digital twin. At the end of the day, everybody talked about a closed loop, like data flow, standardized data format, and we saw a lot of companies showing their own solutions. Let it be like solutions they actually wanted to sell, or they actually created on their own. But at the end of the day, a real closed data chain, standardized data format, and automated handling and flow is still something people are actually researching in and aiming for. And I guess that the seamless integration of both of them is still a few years away. And that's actually the truth for all of the AM processes. Another topic, a lot of research institutions, and that's another part of the story. Here in Germany, a lot of new chairs and institutes on AM have been founded over the course of the last 10 years probably. Also, a lot of the traditional chairs and institutes on conventional manufacturing are switching over to researching and doing stuff in the realm of AM as well. So we're talking about a really large, highly educated workforce being ready for research. However, as we saw, governmental funding actually, let's say, declines a little bit. And there are a lot of industrial applications, but still industry is not picking up as well in the figures needed to actually make sure that we can secure these workforce for the future and make sure that all these topics are and the employees and researchers are still there over the course of the next 20 years probably. So what will be the next point? Process monitoring, control, and sensor fusion. Something people and researchers have been talking about since 10 years, but why is it still a topic? As you can see over here, for the laser powder bed fusion process, you have a lot of different sensors, pyrometry, cameras, whatsoever. And you can throw so many of different eyes on this process and still learn so much about it. And at the end of the day, the customer wants a press, play, and finish machine. So to get the first time right, to increase quality, a lot of groups are actually researching on this, on this topic, let's see, on this topic, but also how can you, for instance, utilize cheaper sensors to achieve a, so to say, probably same results. So in this case, this is a reconstructed geometry just out of camera pictures taken from the powder bed, picture after picture, layer after layer, and afterwards reconstructing the CAD geometry as the part is made. So to see where are the deviances, where do we practically tailor the process on the fly to address deviations on geometry in a cheaper way than actually doing a CT scan afterwards. That's also something researchers are looking into. A next cluster is, and this is especially true for the energy-based processes like laser and E-beam or whatsoever, it's the adaptive process parameters for the increased resolution and precision. What does it mean? So typically, in the old school way, you take the same parameter set for the complete part, regardless of your part geometry, of probably like heat spots which will form because of constrained geometries. Also like, continuous wave for a laser actually being on the whole time, or taking a pulsed wave, so a pulse laser. So there are the tools, there are the ideas, but how can you utilize that in a real press, play, fully way to actually utilize this in those machines? And what you can see over here, just by using process parameters adapted to the geometry, you can get from something like that to something like that to increase geometry and resolution pretty far. So that's something which would be another cluster for research in Germany on the actual side. And AI all along the way. So basically, starting from construction, from design, ending up with what is the sustainability, what are the best parameters for greener building and stuff like that. So as you can see over here, especially again also in the area of process control, taking the information out of the process, handling it, and basically pushing AI into two fields: either big data, too many data actually to work with it in a conventional way, or the other hand is just try to make best educated guesses out of the data that you have. So do not have an expert in the machine, but try to implement the expert in the machine. And what else? Basically, more of everything. So as you saw in the last years, more lasers, optimized stitching, parallel processing, higher productivity, more applications, more materials, multi-materials, all that all along the way is something researchers in Germany actually are looking into and trying to foster the relationship with industry, but also with the end customer, to make sure that AI is something to stay, not only to stay, but actually really to grow and enable in those uncertain times right now. So, and by that, I hope I have represented all of the researchers good enough, and so try to be not specific on one institute or one chair, but basically trying to get a good overview what's actually the biggest topic areas over here in Germany. So thank you for the opportunity.
Tim, thank you very much for your contribution. And right now we start our open discussion here on the panel. Might be we start with a question very specific to Martin, because I know it's pretty late in Australia, you want to go to bed, that's perfectly clear. But might be the first question goes to Down Under. Martin, you have mentioned, and that's perfectly right, in the end, Australia is an island. You're a bloody big island, but you're an island. You're isolated. The biggest
island, the only island continent, far away from all the supply chains, all of these problems.
Exactly.
Or opportunities.
Exactly, that's the question behind the curtain, because you have shown application examples from mainly medicine, life science, defense, but the biggest economy in Australia is mining. Mining followed by education. So are these components, due to the fact that you are far away from all the supply chains, what you have mentioned from a logistics perspective, are there any applications from your biggest economy, mining?
Yeah, absolutely. And I suffer from the same challenge that your other speakers suffer from. 10 minutes is a fairly brief time. We chose to talk about medical, we chose to talk about defense, but we could have also spoken about mining. As you say, one of Australia's substantial slices of the economy. Now, mining in and of itself often focuses on larger components with lower costs. So we're typically talking about weldments. We're not talking about components at the scale of the medical device. Let's talk about things like WAM. You know that our centre has a substantial focus in WAM, so being able to build up large components, potentially with complicated or multi-materials wear resistance plus ductility in large structures, like for instance for earth moving and for mining. Let's talk about things like cladding and refurbishment. So we have an excellent capability in direct energy deposition, for example, for refurbishing hydraulic hardware and hydraulic servos and high-value rail equipment, where we can take a component that's worn and then we can refurbish it back into tolerance and we can put it back into service quickly. Leary is one of our largest collaborators, and their focus is all of these mining applications that we've spoken about. So mining is a very big deal for us. The scale is different. One of the fantastic things about our centre is that we're not really worried about scale. One day we will be building some very fine featured lattice structures for a medical application. The other will be working on mining applications that are 100 times the scale.
Thanks a lot, Martin. So we have 3 incoming questions here from the audience. I will tackle question number, what is it right now? Global challenges such as climate change, energy, sustainability, and public health. And afterwards, Tim, I would ask you to tackle question number, what is it right now?
Probably 1.
Exactly, the German one, German government, because we are absolutely aligned with what comes to the German government in terms of our, let's say, public funding. Or you want to go first? Let's tackle let's tackle that question first, and then we come to a perspective of China, and I tackle the sustainability one.
So whatever you wish. Basically, the easy answer would be money. Always the easy answer is money. But I think if we really dive deep into it, I think it's a strategy. You need to have a strategy with all the stakeholders involved, and to all the ones which are not living here in Germany. So in Germany we have like the federal government as well as the different, let's say, like subdivisions, sub-countries, parts of Germany which have their own funding devices and funding vehicles. And I think it worked pretty good for the time being. But right now, where you have constraints in basically money, in everything, I think there needs to be like a strategy. Because as a researcher, for my AM process, I want my AM process to be able to do everything. Because I'm pretty proud of my technology, right? But at the end of the day, probably the road to the future would be to have a sort of a strategy to really say, this AM process is by itself tailored for these applications. And so probably try to funnel it and try to focus it and to make sure that you're not spending money on areas where it's probably not 100% effective. I know, out of a researcher way, it's not the right answer, but on the other hand, I think with the global content, it might be the right answer probably.
Dongdong.
Yeah.
Can you please tackle the question, can you highlight any breakthrough technologies or materials that are expected to revolutionize industry standards in the upcoming or coming years?
Yeah. So I think this is a very important and interesting question. And I think for the current, first of all, I see something about the name of the additive manufacturing. In China, if we make the direct translation from Chinese to English, we call it additive material manufacturing. So in the Chinese name for this for the additive manufacturing, we take a very high highlight on the material itself. And I think the material issue is very important for the breakthrough and for the innovation of the additive manufacturing technology. Currently, I think the multiple materials is very important for additive manufacturing. That means normally the pure alloy or pure metal, its strength or its ductility is quite limited for the industrial applications. So we can, for example, we can add some ceramic to the metals to produce the component material to enhance the strength and the ductility of the printed parts. This is, I think, this research, I think we have already began more than 20 years ago. And currently, with the development of the equipment of the additive manufacturing, I think the material, the meaning of the material is very broad. That means for the whole components, we can, first of all, we should focus on the different performance requirements. For example, here we need a very strong material, and here we need a soft material, and then we can use the additive manufacturing technology to print different materials in different positions to meet the very comprehensive requirements of the components. Yeah, I think the multiple material printing, this is a very hot topic currently. And then in the future, even for the laser printing of the metals, we can combine the electronic devices into the whole components. So I think the meaning of the material, it will be very, very broad. But anyway, I think the requirements from the industry application, this is very important. And then I think the industry can give us a lot of questions and problems. And then for us in the university, we can focus on the basic research. But I think the question should be from the industry. Yeah.
So demand-oriented and target and product-oriented.
Yes.
Thank you. I would like personally to tackle the question with regard to solving global challenges such as climate change, energy, sustainability, public health. One example was provided this morning by Carsten Häuser. I take that from a personal experience and personal history. If you have in mind that everybody right now worldwide, globally, discusses about hydrogen economy. Of course, you could come to the, let's say, interesting idea to re-electrify hydrogen. You do that by utilization of a gas turbine. And if you would like to utilize a gas turbine burning hydrogen instead of methane, that is usually natural gas, the problem is that the gas turbine needs to burn hydrogen, and hydrogen burns at temperatures that are 200 Kelvin higher, increased in comparison to methane. So what you do is remelting your gas turbine. That is not a clever idea. So what you could do is, of course, redesign your entire so-called hot gas path. Burner components, the burning chamber, the first two high-pressure turbine stages. By doing that, the components do, let's say, in the virtual world, exist. Problem is manufacturability. You cannot manufacture these kind of components because the cooling channels are very fine, are very narrow, are very, very tiny. You cannot manufacture these kind of components by a conventional cast manufacturing route. It is not possible, it's impossible, but you can print them out. So that means that AM is the key enabler, the manufacturing key enabler for, in the end, getting to an H2-ready gas turbine if you think about re-electrifying hydrogen. That's just an example. The first one, Tim, is a German-specific one. Research in Germany seems pretty fragmented. It doesn't seem to be, it is. Everyone, etc. Can you tackle that question?
Yes, so basically, absolutely. So it is fragmented. We have a lot of different players, which is not necessarily bad, because a lot of players actually give a little bit of competition also in the research area and a lot of new ideas. But what we see is to make it sustainable, to keep sustainable, what is already written down there, the larger research clusters, it has to be clusters or initiatives where research meets with industry and end users. And that is something which was founded and then supported, for example, by the BMBF, the German Ministry of Research. actually a few years ago, and there are some ongoing centers in Germany. One is in Aachen, one is in the area of Dresden, and there are other ones in Germany as well. And so basically,
for example, in Hamburg, right?
For example, yeah. And so at the end of the day, it is if you keep industry involved and you make sure that you get a framework which pushes you funded through at least, like, let's say 5 years or so. So the framework can be established, and then that within the network you have more and more collaboration, more and more entrustment, people trusting each other, people sharing, and also people are, even competing companies, are actually finding common ground where to have joint research and share the results, even though actually they are competing. So for example, you talked about turbines. The materials in turbines for gas turbines or flying turbines actually are often pretty much the same. So qualifying these materials and these processes, actually an aerospace company as well as an energy producing company or energy gas turbine producing company actually can find common ground to actually join forces on these topics and then branch out afterwards. And I think that is something which is already done. So not everything is bad. So we have a lot of good initiatives, and I think that within the next 5 years or so, we'll see if these are really sustainable or not.
Thanks, Tim. And there's an Aussie-specific one, Martin. That's for you. What is the key driver for wire arc additive manufacturing in mining industry in Australia, I guess, of course, spare parts on demand, etc.? Would you like to tackle this kind of question?
Okay, so a lot of people come into our facility and they say, this is very interesting, but in terms of parts per hour, parts per dollar, parts per kilo or kilograms per hour, it doesn't suit our particular industry. And many of those industry partners are from heavy industry, agriculture, mining. Now, they're very interested in WAM to give them the flexibility to build components that have all of the flexibility of additive, but the physical size of, say, a weldment. And we're also finding, for example, with collaboration through companies like Leary in mining, that we can lay down some relatively inexpensive, say, mild steel substrates, and then add some fairly exotic materials to those, essentially to put wear-resistant components or wear-resistant features onto components, and essentially have multi-material components at that scale.
Thanks, Martin. Second question, Dongdong, much appreciated if you can tackle that. What are the key trends shaping R&D today, and how will they influence the landscape of industrialization in the future?
Yeah. Normally we say that we can print everything. We can print the whole world. But currently we should see that additive manufacturing actually should combine with different processes. Normally, for the future development of R&D and additive manufacturing, I have two keywords. The first one is that the multiple. For the material itself, we normally can introduce multiple materials for printing, and then for the additive manufacturing process itself, we should combine different processes to get a very high accuracy and a very high performance. Yeah, so we should, I think, the additive manufacturing, either the material or the process, we should combine different elements. And then the second keyword is for the multiple functionality. Yeah, currently for a majority of additive manufacturing, basically we focus on the mechanical properties. So that's why we produce the metals, alloys, and for the load bearing performance. But in future, with the development of material and the process, normally we can, for the whole component, we can introduce more functionality besides the mechanical properties. Yeah. So I think for the future, I think we have a lot of innovative elements for the development of additive manufacturing.
Thanks a lot, Dongdong. I think question number two is specifically yours, Tim.
Again?
Yeah, because you have shown that wonderful process chain, the entire process chain, and I think everybody should be interested in, let's say, coupling the entire end-to-end virtual process chain with the entire manufacturing route. AM is not just a process, AM is an entire manufacturing route in, let's say, the real world. So question number 2 of Gregor Reichle goes out to you. What are the key milestones of R&D activities to enable fully digital qualified additive manufacturing? And I know we could talk about days right now.
Yeah. I think an open data format standard, which really is able to address the complete realm, and which is really open, that would be a key driver. So to put it another way, so as we saw in digitalization and let's say microservices for machine parts, where you have microservices on the camera, on the axes, and all orchestrated by one centralized server. Years ago, that was really like just a very strict and very hardwired framework. But since, for example, Netflix entered the market, and with a load bearing of how many people worldwide are watching this movie and how many virtual service needs to be put up actually to have everybody see its own movie and repeat and fast forward, backwards and whatever. All the orchestration with these Docker services, microservices and so on was really a helpful tool to utilize microservices in machines. And I think that is something which needs to be done. You need to see where other really large applications and companies like Netflix and Google, whatever, lead the way and pave the way for data formats, data standards, which are open source, and then can actually be applied on AM processes as well. And I think that might be something. Cloud solutions, we see it, that is something which is really flying right now, but I think that would be the path forward.
Thanks a lot, and I pick right now the last question and ask everybody of yours just to give a quick statement because we are running out of time, 3 minutes left. So are there any R&D projects that particularly stand out for their potential to provide solutions to these global issues? I guess with global issues is meant fight climate change, demographic change, security defense, that kind of stuff. So might we start with Australia, a short statement from Melbourne, Martin, yours, then Dongdong, then afterwards, that's the final statement of Tim.
Thanks, Ingo.
Martin.
And given that we're low on time, I'll start by saying a big thank you from Professor Milan Brandt. He asked me to pass that on, and thanks to everyone. I think that the comments regarding certification are really relevant, and one area that I think is a substantial opportunity is essentially telltale thermal subcomponents within a build volume that can tell us a lot of information about the quality of the build, but be much smaller, much more rapidly assessed, potentially visually assessed. So very small components that can be attached as essentially witness coupons. That seems to be an opportunity for dramatically reducing the cost for certification and building a process chain that's robust. That's just one comment that I think is worth making.
Thanks a lot, Martin. From a Chinese perspective,
I think for us, I think for our research in the university, we focus more on the basic research to understand some key issues of each additive manufacturing process. That's very important. Also, I think for us, I think the Sino-German cooperation is also very important. So I'm looking forward to have more cooperations on the research, especially basic researchers with German scientists.
Thanks a lot, Dongdong. And Tim, you have 1 minute, 5 seconds, 4 seconds, 3 seconds. Go on, come on.
So basically, just going a different route, I think making sure that different kinds of feedstocks, like different kinds of powders, especially in the metal ream, can be utilized for AM, because that is actually a real driver on reducing greenhouse gas emissions, sustainability, reusability of these powders. I think that's something which is often overlooked whenever we talk about processes and applications, but I think that's also like a big lever.
Perfect timing, my friend. Half a minute left. Thank you very much for that panel discussion, also for your initial statements, 10 minutes each, and of course, good night to Australia, and I'm closing the session right now.